highly complex, fascinating and promising nuclear power unit named Brest 300 OD about to be built in Russia. So what is so unique about this nuclear power plant and why it is crucial for the future of the entire nuclear power industry in the world? On June 8, 2021, in the city of Seversk, Tomsk region, the first concrete was poured at the construction site of the experimental demonstration power unit Brest 300 OD, the new lead cool-fast neutron nuclear power reactor made to demonstrate incomparable and unique technology, a complete closed nuclear fuel cycle. Along with power reactor, fuel cell fabrication plant and a spent nuclear fuel processing facility will be built on the ground. It will make possible for the Brest power unit not only to provide itself with brand new fuel, but also to produce nuclear fuel for other reactors. During the first concrete pouring ceremony, General Director of Rosatom Alexei Likhachov described the significance of the project by saying, "Thanks to the processing of nuclear fuel an infinite number of times, the resource base of nuclear power industry will become almost infinite. At the same time, the problem of accumulating nuclear waste is eliminated for future generations." As of today, no country in the world has these technologies. Russia will become first global powerhouse that will be able to start such a complex and brave project. The very technology of the closed nuclear cycle technology, in theory, is simple, but extremely difficult in implementation. For better understand technology, we'll have to dive deep into the details of the work of a nuclear reactor. Fission of any heavy nucleus, uranium, thorium, or plutonium, emits 2 or 3 extra neutrons, and that free neutrons doesn't live long. Usually free one is absorbed by neighboring atoms, fuel the reactor, or even coolant. If a neutron is absorbed by a reactor structure or a coolant, this leads to controlled radioactivity. Often neutrons turn strong nuclei into unstable ones, sensitive to subsequent breakdown. In conventional light water reactors, such a process causes accumulation of heavy hydrogen isotope tritium in the water coolant. In usual light water reactors, this process causes the accumulation of heavy hydrogen isotope tritium in the water coolant. Tritium then has to be isolated through the complex of manipulations or wait till water from the reactor is naturally cleared off as a result of radioactivity decay. The lead coolant in Brest reactor is radiation resistant and not that easy to activate. It means the liquid lead of which is composed is extremely reluctant to absorb neutrons and basically doesn't accumulate inducted radioactivity. Eventually, in contact with water and air, lead is chemically passive, which excludes chemical and thermal explosion possibility if the primary circuit of the reactor is depressured. In case of leakage of the circuit, lead will simply flow out, cool down, and become solid, closing the leak with such cork. Another important feature of the lead, it is high boiling temperature of 1749 Celsius at normal pressure. Due to extra pressure inside the coolant loop, lead in the Brest reactor circulates at temperature of 1751 Celsius, still being liquid, close to the boiling point. That huge temperature is almost perfect for any thermodynamic cycle that is driven by temperature differences. In particular, the Brest turbine will be able to operate on extreme steam up to 600 Celsius, which is significantly higher than the temperature of steam turbines in modern nuclear power plants, where steam never exceeds 374 Celsius. This will let the Brest 300 OD power unit to have 40–45% higher electric efficiency from units with VVER reactors. In the future, lead energy carrier will make possible to completely get rid of the steam in the second circuit. The high temperature of the lead coolant in the first circuit makes possible to serve a closed cycle gas turbine from it, whose efficiency will be given higher from a steam turbine using ultra-high temperature steam. Use of a lead as a coolant makes it possible to reconnect almost all neutrons emitted during nuclear fission back into the fuel assemblies. The absorption of fast neutrons by uranium-238 is really easy, as uranium-238 is greedy for any high-energy particles flying through it. By capturing a neutron, uranium-238 converts itself into the isotope of another chemical element, plutonium-238Ad, and this is also nuclear fuel, the very basis of all nuclear weapons in the modern world. Ideally, each fission nucleus of uranium-235 gives us 1.25 nuclei of new plutonium-239, which miraculously appear right in the reactor from unsuitable for conversion of fission waste uranium-238. Of course, there's no option to see a full, perfect image in a real reactor. Neutrons are actively captured by the nuclei of other elements in the core: fission fragments, coolant and moderator, control, protection rods, and some of the neutrons simply fly out the core. Therefore, in modern light water reactors, like already mentioned VVER reactors, fuel multiplication factor is 0.4 and 0.7, while much needed plutonium-239 is also formed in them, although not so quickly. Due to its design and special setup of fuels and the use of weakly activated lead coolant, breast power unit makes possible to obtain a much higher fuel reproduction ratio, according to calculations up to 1.2, which is near to the theoretical limit. It means once breast is loaded with a nuclear fuel, we can forget about the needs of the reactor for fresh fuel, and even get around 20% of new fissile material from each cycle inside the reactor. The main obstacle in mastering such a technological masterpiece has always been an engineering complexity of fast neutron reactors. If we simplify the task, then a fast neutron reactor is a much harder thing than a standard power unit that uses slow thermal neutrons and water as coolant. In fast neutron reactors, everything is incomparably more intense: destructive neutron flows, coolant temperature, speed and variety of reactions in the core. Besides, technical difficulties and economic cost of creating a full-scale fast neutron power generation turned out to be a few times higher from conventional reactors, which led to significant lag in their development. That's why so far neutron reactors are more experimental and aren't used widely. Positive effects were seen in the first generation of fast neutron reactors, which used liquid sodium as a coolant. Of 4 countries that started construction of these reactors in the world, only working power units were built in USSR and Russia. At the same time, and even earlier, United States, France and Japan also had large-scale experiments with fast neutron reactors with liquid sodium, but left the race without achieving anything substantial. Today, after successfully mastering technology of liquid sodium in fast neutron reactors, Russia is moving on to the next generation power units that use a much safer and more promising lead coolant. It is indeed energy of the future. Now the availability of uranium-235 has not yet reached critical for the industry amounts, but reserves are not endless. Sooner or later, nuclear power will face a shortage of cheap natural uranium-235, and the breast reactors will be replaceable. If you liked the video, be sure to subscribe and ring the bell.